So what are you seeing the parallel and multithreading
Yes,
browser? Okay, that's good.
and some code and a
Uh,
terminal.
okay, that's good. Yes. This section is more advanced, I would say, depending on your experience with the parallel computing. So we will cover several topics, for instance, basic concepts, just the basics, I would say. And also, you will get some knowledge on the parallel tools for programming in the present topic. We will cover just Python. Yes, so next day we will cover other languages. And also, we will see some tools to monitor the usage of resources. So first of all, here is uh, a rough definition of what is parallel programming. Is the science of writing uh, a code that executes tasks on different compute units that are called cores. And here, the crucial point is that these tasks are executed simultaneously. Yes, this is a key word in this parallel computing topic. So in the past, the computers were shipped with a single core per central processing unit, CPU, and therefore only a single computation could be done at a time. And we call these type of programs serial programs, right? So, but nowadays the computer architectures are more complex than a single core, right? We can have some architectures that look like this, as in this picture here, where you have several cores. I am depicting here just two, but you can have many, yes, like 120 and even more. And the common pattern in this architecture is that all the cores can share the memory, right? And we have a different type of architectures where some cores, yes, share some memory, right? But they can exchange messages among them, right, by using some type of protocol, and they can have a more complex architectures, right? Like here depicting a local memory, but also exchanging the memory across them. So these are more complex architectures, I would say. In the case of Kebnekaise, this is a more realistic picture of what you will get in a standard node. You can see here that we have several cores, up to 14 for this type of nodes, and they can have a different type of a memory that are available to each single core. And there is a hierarchy of memory when you go from here, from this type of memory that is available, yes, to the core, and then you go up, and then all these cores have some available memory that is shared across them, yeah, right? And they are also connected to the so-called socket, right? And in this case, all these cores, the 28, can share the available memory, which is 2 times 64, in total 128 for this type of node. So you can see that this is a more complex architecture for this realistic node. And why should you care about this type of architectures is that depending on how the code is structured and how you parallelize your code, you can have advantage of the local memory, which has a higher bandwidth, yes, than this one here, yes. So we have also other type of architectures. Birgitte mentioned that previously, and these are the so-called graphic processing unit, GPUs. And this is related to the shared memory, but this is much more specific, and it was covered previously. So why parallel programming is needed? You have seen in my previous picture that you have a complex architecture, and in order to take advantage of this type of hardware, you need to make some changes to your code so that your code is aware of all these capabilities. So either you can do the coding by yourself, or you can use some existing packages or libraries that were parallelized by others, so you can take advantage of this type of software. Yeah. So this is how a cluster looks like, as in our cases at UPPMAX, HPC2N, and the other, LUNARC. So we have some login nodes, right? And here are the computing nodes where you will execute the code. And besides parallelizing your code, right, making the code aware of all this hardware, we also need to have a way to submit the jobs, right, to these computing nodes, right? And that's why we have seen the sbatch command, for instance. So I put here some information about using the cluster, because it's important to make let's say, an optimal use of the resources that you allocate, because you can allocate several cores, but use less in your jobs than what you think. Yeah? And this is one of the problems that can be seen when you move your workflow to an HPC, either underusing their cluster or even overusing it. So it's important to monitor the resources that are being allocated, right? And there are tools that are offered at your HPC centers. And here I show you one possible tool, which is very useful even for me, that is called job usage. And if you click on this link, you will see a picture of how it looks like this, right? This picture here is a graphical interface, and here you can see how the resources are being used for some of your simulation, right? You can see the CPUs, the memory, and the GPUs resources. So sometimes, for instance, you can forget to load the proper libraries, and then if you request several cores or even GPUs, then maybe you are not using any of them at all, and you are running a serial code, right? So it's important to inspect how your simulation is running. So other centers can have different tools, and at UPMAX, I think if you have an interactive node session, you can use either the top command of htop, right, to monitor how the resources are being used. So there are different type of programming paradigms, and I will briefly describe all of them, right? Uh, but this is just a brief description, right? And we will cover that for different languages. And in particular, for today, we will talk about specifically on Python. Yeah? So the first model is called threaded programming. So in the picture I showed you before for the shared memory, The key feature was that all the cores could share some memory space. And I mentioned that the bandwidth for this type of memory was high, right? So threaded programming tries to take advantage of this high bandwidth, yes, for the this type of memory, which is local to all the cores. So, in particular, low-level languages like Fortran, C++, use OpenMP, which is a standard API, application programming interface to parallelize programs within the threaded mechanism, right? And we can have several libraries, especially for linear algebra, than behind the scenes for Python or the other languages use OpenMP as a parallelization tool. So here we can tweak the threaded mechanism by setting some environmental variables, and specifically for OpenMP, we can use this flag here to set the number of threads. So higher level languages have their own mechanism to generate the threads, and they can that can be confusing, yes, especially if you are using some libraries for linear algebra, for instance, LabPack, BLAS, FlexiBLAS, or others, yes, and because these have their own mechanism, as I mentioned here, yes, where you can set the number of threads, right? And in particular, this can lead to some issues. So here there are some recommendations when you're dealing with this threaded mechanism. So you can check if the libraries that you're using have a threaded mechanism. For instance, BLAS, OpenBLAS, LabPack, FlexiBLAS, right? You can also check the resources that how they are being used. And I mentioned here one possible tool. Yes, and also you have other tools at your centers to see if you are not overusing the system. So here I listed some possible things that could happen, right? When you are using the threaded mechanism, and specifically for Python today, imagine that you are using a NumPy, and behind the scenes, NumPy is using some linear algebra package, and the variable OpenMP threads is set to some particular value. So if you're using this linear algebra operation in a parallelized process, right? By using n processes and you allocated n cores, right? And in addition to this, you're using some number of threads per process, you will be over exceeding the resources that you requested, right? So this is something that could happen, and it's important that you monitor the resources. And if you use here at our center this tool, you will immediately see a red line where it says that you are using more than 100% of the resources. Here, there is something that happens commonly, especially for this shared memory programming, is a data racing, which means that all the threads can write on the same memory space, and then they can modify the variables or the arrays and that can lead to uh, to some data that is not reliable anymore, right? Because all the threads are modifying the array at the same time. So for Python, here there are some nuances for threaded programming. So Python offers its own threaded mechanism. Yes. And this is not to be confused with the threaded mechanism that the libraries can be using. And I mentioned before one particular example, for instance, for NumPy, which under the hood is using some linear algebra library, let's say OpenBLAS or FlexiBLAS. So this is not the same as the Python threads, right? And there is some way to specify the Python threads, right? However, the Python threads up to now are not efficient for computation because there is some locking mechanism that is acting on them. And but even in that case, if you are doing some I/O file handling, then that could be still useful, right? Because it's not computationally heavy. So that because of that, I will not cover the Python threads anymore. So the second model is called distributed programming, and is related to the second plot that I mentioned previously, where the cores can exchange messages. So if we remember in the shared programming, all the cores have an available or a shared memory, right? Where they can write and read. But this type of architecture is not scalable, right? Because it scales only up to the number of cores within one node. But if we want to scale the code up to hundreds of nodes or even more, then we need something else, yeah? So that the cores can exchange messages across some interconnect. So in this case, we will not use the threads anymore, but we will use the so-called processes, yes? And there are several APIs for doing this messages exchange. And one of them is called Message Passing Interface, MPI. And in general, yes, if you have your code in a higher level language, then you need to refactor your code. And also, most likely, you need to change the paradigm for programming. So here there is some specific nuance for the distributed programming for Python. So Python has a different module for achieving distributed programming. For instance, multiprocessing and MPI for Py. So in this case, for multiprocessing, you don't need to install any module because multiprocessing is shipped with the standard library. But in this case, you need to do some installation and also to do some settings, right? So that you can use MPI with Python. I included also some information for big data. So you have some arrays that are big enough so that they don't fit the size of a single core or the size of your machine. So in these higher level languages, there are already some tools to deal with this big data. And in particular, for Python, there is a tool called Dask, uh, which has several features. For instance, it can interact with NumPy, with pandas and machine learning libraries like scikit-learn. And essentially, the philosophy of Dask is to divide the array into small pieces, and also it performs some lazy computing. So the tasks are not done right away, but they are queued and they are only executed at the moment that you want to fetch the result, right? So this is a more complex topic, Dask, and here you can find a Jupyter notebook, right? We won't cover Dask today. We have an additional Python course specifically for HPC that is also a part of the NAISS training program. And we will cover this in more detail in that course, but not today. So I will go to a quick demo and show you how to do some parallelization task. And this is especially useful for research, right? Because in general, we have some for loop, yes, that is requires extensive operations for each iteration. So this is language agnostic, and essentially we have a loop that goes from 1 to 4. Yes, this is just a simple example. And here inside the loop, we want to perform some task. In this case, we want to wait just 1 second and then finish the loop. So how it looks like, so we have some tasks which are reflected in this wait operation that can be more complex, but here we are saying that just wait 1 second to mimic some more complex task. And because we have four, so it will take 4 seconds in total if we run on a single CPU. But if we divide this task into four CPUs or four cores, right? Then on average, it will take around 1 second, right? Because we are partitioning this block here into four pieces. So for that, we can use Python, and here we can call the script is sleepy.py. And sleep function is mimicking this waiting time for 1 second, right? So you can have here the Python script that you can copy, right? And then you can paste in your script. Yes, I did it. Let me see, it's here. And essentially, it's the same script. As you can see, we have four iterations. We will be employing multiprocessing in Python that I mentioned previously. So here you have a function for the serial program that we can write as a for loop, and then we wait for 1 second. So, but if we want to parallelize this function, what we can do is to divide the workload, which in this case is the number of iterations, and then we specify the beginning and the end for the workload of each process, right? And then we execute this loop just for the beginning and the end for each process, as this is here. So as you can see here, we need to reflect the parallelization of the serial function into some new parallelization paradigm, right? That reflects the fact that we have now several processes. After that, we take timings for the serial and the parallel processing and print out the results, yeah, and the timings. So to do this, we can load these modules. I'm doing this for Kebnekaise, but you can do it. You can do that for the other machines. And right now, interesting, the server is low. And it was not like this a few minutes ago. Interesting. Do you know if there is any issue with the login node, Brigitte?
There shouldn't be, but I mean, I have also had glitches where programs doesn't run for several attempts. But I know there was a problem where the /temp directory was full earlier today, and that caused problems with logging in. And if it is full again, I could well imagine that that also could give problems, and that is on the login node.
Yeah, because I cannot even see my cursor there, which is annoying. So, you need to load these modules and then execute the command by running this srun command. Here you type -a, your project, and then specify the number of task, the number of cores, in this case is 4, the time, and here you execute the Python script. So this will show you that on average, this takes 1 second for the parallel process using 4 processes and 4 seconds for the serial program here. Yeah. But at this point, I cannot show you this because it's not working for me.
Okay, I can say that there are problems on the ThinLink login node. Where people are going out of memory or something. They think it's someone who is running heavy Matlab jobs directly on the login node, which
I
is
see.
causing problems.
I see. Okay, then we can go to the exercises, and here you will learn how to run a code uh, efficiently, I would say, and this is a 2D integration problem. So this is the way to compute an integral, right? And essentially, we divide the integration into the so-called bins or in a grid, right, for the x and y directions. And then we divide the integration only on the x axis. So you don't need to perform the parallelization. It's already there, but you need to run the code. And here is how you will parallelize this program. So you can see here it's more complex than doing a simple for uh, loop, because here you need to divide the workload across the different processes. But essentially you need to modify here the number of processes and this fix me. Yeah, and then run the script by using different cores. Yes. And notice that this number should be the same in both the batch script and the Python script. Yes. So this is the point where you can have overusing and or underusing of the cluster. For instance, if you specify here more workers than what you allocate here on the batch script or the other way around, right? So you need to keep in mind this thing here. And this is more advanced, it's more, but also more realistic, where you have a data frame, you divide the pieces of work across the different workers so that you can do some computation like an average. Okay, let's have some 10 minutes for the first exercise, and you can see if you can do the second one, right? So now my pin link seems to be back. Yeah. So let's try this first exercise. Yeah. And we will have until when?
15:45.